Welcome to Object-Oriented Programming in Python. OOP is a fundamental programming paradigm that lets you structure code around objects and classes. Today we'll master the building blocks of OOP: classes, objects, attributes, and methods. By the end, you'll understand how to design and create your own custom data types. Object-oriented programming is a way of organizing code around objects rather than functions and logic. Objects are bundles of data and functionality. Think of them as real-world entities with properties and behaviors. Imagine a car. A car has properties like color, brand, and current speed. These are its data. A car also has actions like starting, accelerating, and braking. These are its methods. In OOP, we bundle these properties and actions together into an object. The car is the object, and its properties and methods define what it is and what it can do. Understanding the difference between classes and objects is crucial. A class is a blueprint or template. An object is a specific instance created from that blueprint. Think of a class as a cookie cutter and objects as the actual cookies. On the left is the class, our blueprint. It defines what properties and methods cars have. On the right are objects, actual car instances created from the blueprint. Each object has the same structure but can have different values. Car 1 is a red Toyota. Car 2 is a blue Honda. Car 3 is a green Ford. One class, many objects. This is the power of OOP. Let's create our first class in Python. We use the class keyword followed by the class name. By convention, class names use Pascal case, where each word starts with a capital letter. Here's the simplest possible class. The class keyword defines a class named dog. The pass statement is a placeholder that does nothing. This class is empty but valid. Now we have a blueprint for dogs, even though it has no properties or methods yet. To create an object from a class, we call the class name with parentheses like a function. This creates an instance. Here, my_dog is an instance of the dog class. We can create as many dog objects as we want from this single class blueprint. The __init__ method is special. It's called automatically when you create a new object. This is where you initialize the object's attributes, setting up its initial state. Think of __init__ as the setup instructions for your object. Let's break this down. The __init__ method takes parameters. The first parameter is always self, which refers to the instance being created. Then we have name and age, which are values we want to pass when creating a dog. __init__ with double underscores is the constructor method. It runs automatically when you create an object. Self represents the specific instance being created. Name and age are parameters you provide when creating the dog. These let you customize each dog object. The self parameter is crucial but often confusing for beginners. It's a reference to the current instance of the class. When you call a method, Python automatically passes the instance as the first argument. Let's visualize this. Imagine 3 dog objects: dog 1, dog 2, and dog 3. When you call a method on dog 1, self refers to dog 1. When you call it on dog 2, self refers to dog 2. Self is like saying, this specific object right here. It allows each instance to maintain its own separate data while sharing the same methods. Attributes are variables that belong to an object. They store the object's data. We create attributes using self-dot notation inside __init__. Each object gets its own copy of these attributes with potentially different values. Here we create 3 attributes: name, breed, and age. Self, name means this object's name. Self, breed means this object's breed. Each dog object will have its own name, breed, and age. The values come from the parameters passed during object creation. Now we create 3 dog objects with different attributes. Buddy is a 3-year-old golden retriever. Max is a 5-year-old beagle. Lucy is a 2-year-old poodle. Each object is independent with its own data. This is the power of attributes. Same structure, different values for each instance. Once you create an object, you access its attributes using dot notation. This lets you read or modify the object's data from outside the class. Use the object name, a dot, then the attribute name. Buddy, name gives us Buddy. Buddy, breed gives us golden retriever. You can also modify attributes directly. Buddy.age equals 4 changes Buddy's age. This dot notation is fundamental to working with objects. Methods are functions that belong to a class. They define what objects can do. Their behaviors. Methods can access and modify the object's attributes. And they always take self as the first parameter. Here we add 2 methods. The bark method makes the dog bark. Using the dog's name, get_age_in_dog_years calculates the dog's age in dog years using the age attribute. Notice both methods use self to access the object's attributes. Methods bring objects to life by giving them actions they can perform. To call a method, use dot notation just like accessing attributes. But include parentheses. Python automatically passes self, so you don't need to provide it. We call Buddy, bark, with parentheses. Python automatically passes Buddy as self to the method. The method executes using Buddy's data and returns the result. You never manually pass self. Python handles it behind the scenes. This makes method calls clean and intuitive. Methods can take additional parameters beyond self. These parameters let you pass information to the method when you call it, making methods flexible and powerful. The learn_trick method takes a trick parameter. It adds the trick to the dog's tricks list. Perform_trick also takes a trick parameter and checks if the dog knows it. These methods combine the object's data with new information you provide. Parameters make methods interactive and adaptable to different situations. We call learn_trick with different tricks as arguments. Buddy learns to sit and roll over. When we call perform_trick, Buddy performs tricks he knows and reports tricks he doesn't. The method behavior adapts based on both the object state and the parameters provided. Let's build a complete, practical class that brings together everything we've learned. Initialization, attributes, and methods working together. We create a bank account class. The __init___ method sets up the owner's name, starting balance which defaults to 0, and an empty transactions list. These attributes store the account's state. The deposit method adds money to the balance if the amount is positive. It records the transaction and returns a confirmation. The withdraw method checks for sufficient funds and valid amounts. It deducts from the balance and logs the transaction. These methods modify the object state safely. Get_balance returns the current balance with the owner's name. Get_transaction_history returns all transactions as a formatted string. These methods provide information about the object state without modifying it. Now let's see our bank account class in action. We'll create an account and perform various operations to demonstrate how all the pieces work together. We create an account for Alice with a starting balance of $1,000. We check the balance, deposit $500, withdraw $200, and try to withdraw more than available. The account maintains its state correctly, validates operations, and provides clear feedback. This demonstrates a well-designed class in action. There are two types of attributes: instance attributes and class attributes. Instance attributes are unique to each object. Class attributes are shared by all instances of the class. Species is a class attribute defined outside __init__. It's shared by all dog instances. Name and age are instance attributes defined inside __init__ with self. Each dog has its own unique name and age, but all dogs share the same species value. Buddy and Max have different names because those are instance attributes. But both have the same species because that's a class attribute. You can access class attributes through instances or through the class itself. Use class attributes for data that should be the same for all instances. The __str__ method is another special method. It defines how your object appears when converted to a string or printed. Without it, printing an object shows a cryptic memory address. With it, you control the display. Without __str__, printing a dog object shows an ugly memory address. This isn't helpful. Users can't understand what the object represents just by looking at it. With __str__, we define exactly how the object should appear. Now printing Buddy shows a clear, readable representation with the dog's name and age. This makes debugging easier and provides better user experience. Always implement __str___ for your classes. Let's build a practical student class that demonstrates all OOP concepts together. This example shows how to structure a real-world class with proper initialization, attributes, methods, and string representation. Our student class has a class attribute for the school name shared by all students. Instance attributes include the student's name, ID, grade level, an empty courses list, and an empty grades dictionary. This initialization sets up the student's data structure. The enroll_course method adds a course to the student's list if not already enrolled. Add_grade assigns a grade for a course, but only if the student is enrolled in it. These methods validate data and maintain consistency in the student's records. Get_GPA calculates the student's grade point average from all course grades. The __str___ method provides a clean summary showing the student's name, ID, grade level, and GPA. This makes student objects easy to understand when printed or logged. Now let's use our student class to demonstrate how all its features work together in a realistic scenario. We create a student named Alice Johnson. She enrolls in 3 courses: mathematics, physics, and English. We add her grades for each course. The GPA calculation shows she's averaging 91.67. Printing Alice shows all her information in a clean, readable format. This demonstrates a complete, functional class managing complex data. Encapsulation is a fundamental OOP principle. It means bundling data and methods together and controlling access to that data. This protects the object's internal state from invalid modifications and makes code more maintainable. Notice the underscore before balance. This indicates it's a protected attribute. Users should access it through the get_balance method, not directly. Methods like deposit ensure only valid operations occur. This protects data integrity and allows you to change internal implementation without breaking external code. Encapsulation makes code robust and maintainable. Python uses naming conventions to indicate attribute visibility. Public attributes have no underscore. Protected attributes have one underscore. And private attributes have two underscores. This is a convention, not strict enforcement. Public attributes have no underscore and are meant for external use. Protected attributes with one underscore signal internal use only, though they're still accessible. Private attributes with two underscores undergo name mangling, making them harder to access from outside. These conventions help developers understand how to use your classes properly. Properties provide a Pythonic way to implement getters and setters. They let you access methods like attributes, adding validation or computation while maintaining clean syntax. The @property decorator turns a method into a getter. The @Celsius.setter decorator creates a setter with validation. Now you can access Celsius like an attribute, but it runs the method with validation. Fahrenheit is a computed property calculated from Celsius. Properties make your API elegant while maintaining control. Using properties feels natural. Access Celsius and Fahrenheit like normal attributes. Setting Celsius triggers validation automatically. Invalid values like -300 raise errors. Users get simple syntax while you maintain complete control over the data. Besides instance methods, Python has class methods and static methods. Class methods work with the class itself, not instances. Static methods are utility functions that belong to the class logically but don't need instance or class data. Class methods use class method decorator and take CLS as the first parameter, representing the class itself. Margarita and pepperoni are factory methods creating specific pizza types. Static methods use static method and take no special first parameter. Is_valid_topping is a utility function related to pizzas but not needing instance or class data. Class methods provide convenient factory functions. Pizza, Margarita creates a margarita pizza without manually specifying toppings. Static methods work like regular functions but live in the class namespace. They're useful for utility functions related to the class concept. Objects can contain other objects as attributes. This is called composition. It models has a relationships. A car has an engine. A person has an address. Composition creates complex systems from simpler components. We create an engine class with horsepower and a start method. The car class has an engine attribute that's an engine object. This is composition. Car has an engine. The car's start method delegates to the engine's start method. This creates modular, reusable components. Creating a car automatically creates its engine. Starting the car starts its engine internally. You can also access the engine directly through the car object. Composition makes complex objects manageable by breaking them into smaller, focused components. Let's build a complete library system that demonstrates all loop concepts. Multiple classes, composition, encapsulation, and methods working together in a realistic scenario. The book class represents a library book with title, author, and ISBN. It tracks checkout status and provides methods to check out and return books. The __str___ method shows book information with current availability status. Now let's create a member class representing library members who can borrow books. The member class has a name, ID, and list of checked out books. Checkout_book enforces a 3-book limit and adds books to the members list. Return_book removes books from the list and updates book status. This demonstrates managing relationships between objects. Finally, the library class manages the entire collection and membership. The library class manages books and members' collections. It can add books, register members, and query available books. This top-level class coordinates the entire system, demonstrating how multiple classes work together in object-oriented design. Let's see our complete library system in action with all classes working together. We create a library, add books, register a member, and perform checkouts. All classes interact seamlessly. Books track their status, members manage their checkouts, and the library coordinates everything. This demonstrates the power of object-oriented design. Complex systems built from simple, focused components working together. Let's review why object-oriented programming is so powerful and widely used. OOP provides numerous benefits that make code more maintainable, reusable, and easier to understand. Modularity organizes code into self-contained, focused units. Reusability lets you use classes across multiple projects. Encapsulation protects data from invalid modifications. Maintainability means changes are localized to specific classes without affecting others. Abstraction simplifies complex real-world systems into manageable models. These benefits make OOP ideal for large applications. Good object-oriented design follows key principles. These guidelines help you create classes that are flexible, maintainable, and easy to understand. Single responsibility means each class does one thing well. Don't repeat yourself promotes code reuse through classes. Keep it simple avoids unnecessary complexity. Composition over inheritance favors building objects from components. Program to interface focuses on what objects do rather than implementation details. Following these principles creates better software. Let's examine common mistakes beginners make with object-oriented programming and how to avoid them. Learning from these errors will make you a better OOP developer. Avoid God objects that try to do everything. Break large classes into smaller, focused ones. Avoid tight coupling where classes depend too heavily on each other. Always validate data before storing it in objects. Implement _str__ methods for readable output. Use encapsulation to protect internal state. Recognizing these mistakes helps you write cleaner, more professional code. Object-oriented programming isn't always the best choice. Let's understand when OOP shines and when simpler approaches might be better. Use OOP when modeling real-world entities like cars or bank accounts. It's great for large systems with many interacting components. Use it when code will be reused or maintained by teams, however. For simple scripts, data pipelines, or mathematical computations, functional or procedural approaches may be simpler. Choose the right tool for each situation. Let's test your understanding with a practice exercise. Try to build a rectangle class before looking at the solution. This will solidify your OOP knowledge. Create a rectangle class with width and height attributes. Add methods to calculate area and perimeter. Include a method to check if the rectangle is a square. Implement __str__ for readable output. Validate that dimensions are positive numbers. Try it yourself before seeing the solution. Here's a complete solution to the rectangle exercise demonstrating all the concepts we've learned. The solution validates positive dimensions in __init__. It provides methods for area, perimeter, and square checking. The __str__ method adapts output based on shape. Testing shows it works correctly for both rectangles and squares. This exercise demonstrates proper class design with validation, methods, and readable output. You've mastered OOP basics, but there's more to learn. Here are advanced topics to explore next as you continue your object-oriented programming journey. Explore inheritance to create class hierarchies. Learn polymorphism for flexible code. Study abstract classes and interfaces for defining contracts. Master design patterns like singleton and factory. Understand solid principles for professional quality design. Each topic builds on what you've learned today, deepening your OOP expertise. Let's summarize the essential concepts you've learned today. These are the foundations of object-oriented programming that you'll use throughout your coding career. Classes are blueprints. Objects are instances created from those blueprints. __init __ initializes objects with their starting data. Self always refers to the current instance. Attributes store object data. Methods define object behavior. Encapsulation protects data through controlled access. Composition builds complex objects from simpler components. Object-oriented programming makes code modular, reusable, and maintainable. These fundamentals form the foundation of professional software development. Before we conclude, here are practical tips that will help you write better classes from day one. These guidelines come from real-world experience and professional best practices. Start with simple classes and add complexity only when needed. Write clear doc strings documenting purpose and usage. Always validate input to prevent invalid object states. Keep methods short and focused on single tasks. Test classes thoroughly with various inputs. Use meaningful, descriptive names that reveal intent. Always think from the user's perspective. How will someone use your class? These practices separate amateur code from professional software. Continue your OOP journey with these valuable resources. They'll deepen your understanding and expose you to advanced concepts and real-world applications. Read books like Python Crash Course for practical projects and Fluent Python for deep dives. Take online courses from Real Python or Coursera for structured learning. Practice by building actual projects using classes. Contribute to open source to see professional OOP in action. Study source code from popular libraries to see expert design. Each resource strengthens different aspects of your OOP skills. Here's your challenge to cement your learning. Build a complete class from scratch using everything you've learned today. This is how you truly master object-oriented programming. Build a shopping cart class that manages items with name, price, and quantity. Implement methods to add and remove items, calculate total price including any discounts. Display the cart contents in a readable format. For bonus points, add tax calculation and item categories. This challenge encompasses all OOP concepts: initialization, attributes, methods, validation, and string representation. Take your time, plan the design, and build something you're proud of. Congratulations! You've learned the foundations of object-oriented programming. You understand classes, objects, attributes, methods, encapsulation, and composition. You have the tools to build complex, maintainable applications. OOP is fundamental to modern software development. And you've just taken a huge step in your programming journey. Be proud of what you've accomplished. Don't just watch this tutorial, start coding immediately. Create your own classes. Model real-world objects around you. Build complete projects using OOP principles. Every class you write strengthens your skills. Practice is the only way to truly master object-oriented programming. Start small, build confidence, then tackle bigger challenges. You've got this. You've completed your journey into object-oriented programming. You now understand classes, objects, attributes, and methods. You can build amazing software using these powerful concepts. Keep practicing, keep building, and keep learning. The world of OOP is vast and exciting. Thank you for learning with us. And happy coding. Now go build something incredible with object-oriented programming.